Let's look at graphical methods for describing data distributions. So a variable is any characteristic whose value may change. It varies from one individual to another. Your political affiliation, number of textbooks purchased, distance from home to college, where the data are these actual values for a variable from an individual observation, such as a Democrat, Republican, number of textbooks, 1, 2, 3, 4, the actual distance from home to college, 25 miles, and so on. Suppose that a PE coach records the height of each student in his class. Because we're only looking at one variable, this is an example of a univariate. It consists of observations on a single variable made on individuals in a sample or population. Well, now suppose that the PE coach wants to record height and weight. This would be an example of a bivariate data because it consists of pairs of numbers from two variables from each individual in a sample or a population. What if you wanted to add on number of sit-ups and number of push-ups? Now this becomes multivariate because it consists of observations on two or more variables. Let's look at the two different types of variables. We have categorical and numerical, where a categorical variable is qualitative. It consists of only categorical responses. So which of these variables would not be a categorical variable? I have a car model, birth year, type of cell phone, your zip code, which club you have joined. They're actually all categorical variables. Numerical variables are quantitative. These are observations or measurements taking on numerical values, and it makes sense to actually perform some kind of math on them. So your GPA, heights of students, codes to combination locks, number of text messages per day, weight of textbooks. Wait, which one of these would not be numerical? Even though a code to a combination lock is numerical, numbers, but it doesn't really make sense. Do you want to average or do you want to add combinations? Within numerical variables, there are two types. There's discrete and continuous. Discrete is isolated points along a number line. Usually you think of things you can count on your fingers. Example, number of textbooks purchased. A continuous variable is one that can be any value within an interval, and typically these are measurements, things that you measure. For example, a GPA. So if we measured something, even time, we could say you were 3 minutes late. Well, no, you weren't. You were 3 minutes and 4 seconds. Well, no, you weren't. You were 3 minutes, 4 seconds, and 14 milliseconds. And you could go on and on and on, and that's why measurements are continuous. So let's identify the following variables. The color of cars in the teacher's lot. Definitely categorical. The number of calculators owned by students at your college. Well, this would be discrete and numerical. The zip code of an individual, categorical, that puts people in areas that they live in. The amount of time it takes students to drive to school, this would be continuous, numerical. The appraised values of home in your city. Is money a measurement or is it a count? It's actually a measurement, numerical, but it's a discrete measurement because we don't go past cents. All right, this table that I'm going to show next is just a very good way to figure out how to graph data. So we have all these different graphical displays that we're going to talk about each one, and then we have our variable type. So you can see the majority of these are univariate data, and then the data type, and of course the purpose. Graphs are wonderful because otherwise you just have a big pile of data that you go show your boss and it makes no sense, right? And so what we're looking at here is one thing, what types of graphs can be used with the categorical data. So I can see all the categorical data are just the bar charts. But then also we're going to go further with this and see how the various graphical displays for univariate numerical data compare. So we're going to want to make comparisons. So let's look at the bar charts. A bar chart is just simply a graphical display for categorical data. When do you use it? Univariate categorical data. So to comply with new standards from the U.S. Department of Transportation, helmets should reach the bottom of the motorcyclist's ears. So data was collected by observing 1,700 motorcyclists nationwide at selected roadway locations. Each time a motorcyclist passed, the observer noted whether the rider was wearing no helmet, a non-compliant, meaning a helmet and it didn't go past their ears, or a compliant helmet. And they collected their data, and here's their data. This is called a frequency distribution. A frequency distribution is a table that displays the possible categories, so there's my 3 categories, along with the frequency. Okay, so the count, this is like doing a little tally sheet and then adding up, getting the total frequencies. The frequency for a particular category is the number of times that category appears in the data set. When you add all of these up, you should get the total number of observations, which we do, which was 1,700. A relative frequency for a particular category is the proportion. So in other words, the frequency over the total number of observations. So this first one would be 731 over 1,700. The next one would be 153 over 1,700. The next one would be 816 over 1,700. And I get decimals, and when I add these, I should get 1 because this is decimal of 100%. Sometimes due to rounding, you might get like 0.99999, okay? And typically what you do is you round each one of these, so your rounding does become 1. Well, how do you construct a bar chart? You draw a horizontal line, you write the categories, so the categories are your x-axis. Your y-axis is going to be your frequency or relative frequency, and then place a rectangular bar above each category, and their height is the height of the frequency or relative frequency. All the bars should have the same width, so you're not, doing this line with statistics, making things look weird, and they should be proportional to the frequency or relative frequency of their corresponding category. What we look for in a bar chart is to see how something happens very frequently or very infrequently. So if we graph the motorcycle data, we can certainly see that the compliant is happening frequently, the non-compliant is happening very infrequently, and actually no helmet is showing up very frequently. Let's see what a comparative bar chart is. It's what it sounds like, where you're comparing 2 or more groups. When to use these, we have univariate categorical data, but for 2 or more groups. We construct it the same way, where we have our horizontal as our categories, our vertical is our frequency. But usually what we do is each group has a different color, so we color code them. And in this case, we use relative frequencies on the vertical axis. Can you think of why? Why would we use relative versus counts? Well, in this case, to be able to make meaningful comparisons, because maybe you ask 2 groups. One group you only had a sample of 100 people, and the other group you had a sample of 1,000 people. So your frequency would be way skewed and it wouldn't make sense, so you'd want to look at the actual relative frequencies. Each year, the Princeton Review conducts a survey of students applying to college and of parents of college applicants. They were asked, high school students, ideally, how far from home would you like the college you attend to be? Probably really far away, huh? They also asked parents. Now notice here they asked 12,715 high school students, but they only asked 3,007 parents. They asked them the same question, but how far from home would you like the college your child attends to be? So you can see the frequency, the counts of the students versus the parents. So if I graphed these, they're going to be quite different, right? Because I'm looking at counts here and the sample sizes are so different. So what I want to do is I want to change all of these. So every one of these I want to change into a relative frequency. So I take the frequencies by the total number of students. I take the frequency by the total number of parents. And now I can graph my comparative bar chart. So you can see the comparison that certainly it looks like parents want their kids to live closer to home. I'm sure that has to do with money, not that they really want them close to home, right? Let's look at some different type of graphs that are for displaying numerical data now. A dot plot. When to use univariate, so we still have just one variable, but numerical data. How do you construct it? You draw a horizontal line and you mark it with an appropriate number scale. You locate each value in the data set along the scale and represent it with a dot. So you just have this x-axis kind of thing, and then if there's a value on that axis, you put a dot. If there's a repeated value, you just start to stack the dots. What we look for is a representative or typical value. We want to see if they kind of center, the data set has a center, or are they really spread out, which gives us this shape of our distribution. It also tells us if there's some very unusual values. Are there gaps in the data? Or is there what's called an outlier, which is an unusually large or could be very small data value? And we'll talk about later, what do you do when you have outliers? So what we look for with univariate numerical data sets are similar for dot plots, stem and leaf displays, and histograms. All three of these, you look for the same thing. We're going to really concentrate more on histograms, but let's just go through the dot plots and stem and leaf so you can see what they look like. So Professor Norm gave a 10-question quiz last week in his introductory statistics class. The number of correct answers for each student is recorded below. So the first thing I do is I draw a horizontal line with an appropriate scale. So I draw with the number of correct answers. I could go from 0 to however high I need to go, 10, because it's a 10-question test. The first three observations are plotted. So remember, when you have a repeat at this 6, you stack them. So I plot 6, I plot 8, and I plot 6. I continue to do this until I get the dot plot completed. Now, if you look at this, you can see what's kind of nice to see here is the majority of the students got about 6 answers correct. There wasn't very many that got up to 9. Of course, nobody got them all correct. And there wasn't very many that didn't get the little bit, you know. In other words, there wasn't any 1s or 2s. There was this one person that got 3, but pretty much everybody centered around these values from 5 to 8. So let's look at this again, and the number of correct answers recorded. What we're looking for here is a typical value, okay? And our typical value is the center, because that's what's happening the most. It's pretty easy to see with this dot plot because it's going to be the highest value. And again, we can see that's about 6. There's not a lot of variability. They're all pretty much together here. The center for the distribution is about 6 with very little variability, and it's pretty symmetrical. Symmetrical meaning that if I went right here down the middle and I put a mirror, the left side looks just like the right side, pretty much. It may not be exact, but it's pretty close that it looks symmetric. What I could do is I could draw a curve over these and smooth this curve out, shade this in, and I would see there's only one peak. Distributions with a single peak are said to be unimodal. Distributions with 2 peaks, bimodal, and with more than 2 peaks are multimodal. Think about when you might have something that's bimodal. I mean, I could think of something like shoe size of men and women. They're going to be different averages, right? The average woman's shoe size is, I believe, a size 8. Well, the average for a man might be a 10. And so you would have a peak at 8 for women and a peak for 10 for men. A comparative dot plot, once again, univariate, numerical. The big difference here, you have 2 or more groups. You still do it with your horizontal and numerical scale, but you need to be sure to include group labels for the dot plots. What you're looking for, well, if it's 2 or more groups, you're looking to compare. You're looking at a comparison. So here, once again, in another introductory class, the professor also gave this 10-question quiz, and here's the results. Create a comparative dot plot with the data sets from the 2 statistics classes. So as you can see, here's Professor Skew, here's Professor Norm. Professor Skew apparently has this little dud out here. Is this distribution symmetric? Doesn't look like it, huh? Looks like it's kind of has a lot more data here to the left. So notice that the left side or lower tail of the distribution is longer than the right side. So this is what it means to be negatively skewed, or skewed to the left. Distributions where the right tail is longer than the left is said to be positively skewed, or skewed to the right. So the direction of the skewness is always in the direction of the longer tail. So we can see this heads out, more of the data is heading out to the left. The center of the distribution for the number of correct answers on Professor Skew class is larger than the center of Professor Norm's class, but there's more variability in Professor Skew's distribution. Professor Skew also has this unusual observation where one student only had 2 answers correct, while there were really no unusual in Professor Norm's. These were all distributed nice together. Professor Skew has a negatively skewed distribution, where Professor Norm's is actually more symmetrical. Let's look at another type of display, a stem and leaf. These displays are an effective way to summarize univariate numerical data when you don't have a really large data set. What we do is we split each observation into 2 parts. The first digit is called the stem, and the other digits are called the leaf. So again, this is univariate numerical data. We select 1 or more of the leading digits for the stem, and then we list the possible stem values in a vertical column. Be sure you're doing this from the smallest to largest. Record the leaf, the rest of it, for each observation besides the corresponding stem value. indicate the units for stem and leaves someplace in the display. What we're looking for, again, we're looking for a center, a typical value. We're also looking to see if the data is spread out. We're also looking for outliers and to see if there's any symmetry, as well as if there's a lot of peaks in the data. All right, Going Wireless reported the estimated percentage of households with only wireless phone service for the 50 U.S. states and the District of Columbia. Here's for the 19 eastern states are given here. So this is the percentage of household with only wireless phone service. So what's the variable of interest? The wireless percent. A stem and leaf display would be appropriate here because it's a small data set. You could also use a dot plot. So the 5.6%, these are percentages, I'm going to let this be represented as 5.6%. So all the numbers have 2 digits, because I notice when I get down here, these are going to start to have 2 digits in front of the decimal. So in other words, I'm going to go from 0.5 to 20. Would be way too many stems here. So if I just go from 0 to 2, and I'm just looking at this first value, then I'm not going to have this huge vertical column here. So I'm just going to use the first digit as our stem. The leaf then will be the last 2 digits. So the 5.6, my leaf part would be the 5.6, the 5.7, and so on. So what would the leaf for 20.0% be, and where would it be written? Well, we've said this first value here is my vertical, and so then what's left over is the 0.0. Completing the stem and leaf, going through and putting all these values. The only problem with this, because of all these decimal points in here, this is a little difficult to read. So what you could do, you could drop, once you have these listed, you could drop everything but the first digit, and it just makes it a little easier to read. It does not change the overall distribution of the data set. Certainly it's not necessary to write these in order from smallest to largest, but by doing so, the center of the distribution is certainly easier to see. So meaning I go back and I put these in order. And then don't forget, you need to list what this means, where in this case my stem is my 10s and my leaf is my 1s. And let's talk about this distribution. So I can see the center of the distribution is around this 11%. There's not a lot of variability. They're all pretty much here together. It definitely appears to be unimodal. There's one peak right here, symmetric, and no real big outliers. I can do a comparative where I compare 2 or more groups. I do the same thing. I list the leaves for one data set, and the other one I'm going to put to the right. So I have my leaves on the left, I have my leaves on the right, and again, be sure to include labels. So here's another 13 western states are given here. I'm going to create a comparative stem and leaf display. And what I do here is I put my western states on the left, my eastern states on the right, and so now I can easily compare these, and I can say, well, it looks like the center of the distribution for the western states is a little larger than the center for the eastern states, but both distributions are symmetrical with approximately about the same amount of variability. Histograms, these are the big ones. This is the most important one that we're going to use a lot in this class. The dot plots and the stem and leaf, they're okay when you have a smaller data set, but histograms are for when you have very large data sets. They're univariate, they're numerical. You construct these differently if you have discrete versus continuous. So if you have discrete, this is from counting, remember, each observation is a whole number. So we draw a horizontal scale and we mark it with the possible values because they're discrete values. We draw a vertical scale and we mark it with the frequency or relative frequency. Above each possible value, draw a rectangle centered at that value with a height corresponding to the frequency or relative frequency. We're still looking for a center, a typical value. We're still looking for a spread. We're still looking at the shape of the distribution, the peaks, gaps, and outliers. We're still looking for the same thing that we've been looking for. So queen honeybees mate shortly after they become adults. During a mating flight, the queen usually takes multiple partners, collecting sperm that she will store and use throughout the rest of her life. So a paper provided the following data on the number of partners for 30 queen bees. If I do a dot plot, here's the dot plot of the data. So here's the number of partners. The variable is the number of partners is discrete. So to turn this into a histogram, we already have our horizontal axis here. What we need to do is add the vertical axis, which is our frequency. And then we construct the bars, we center them over the discrete data values, and then their height is the height of the frequency value. So you can see that they're being centered here. And this is the big difference with the bar charts, is that these actually connect, where a lot of times bar charts you could have space in between them. So in practice, histograms for discrete data only show these rectangular bars. So we built the histogram on top of the dot plot to show that they're centered over discrete values, and the heights are the frequency. The distribution for the number of partners of queen bees is approximately symmetrical and centered around 7, and there doesn't seem to be a lot of outliers. If I look at the two histograms here, where one is frequency and one is relative frequency, notice there's no difference. And this is important. This is why we like to do the relative frequency, as you're going to see with these. We're not changing the distribution of our data, and this is very important that you understand that when we switch these to relative. Let's look at histograms with equal width intervals. Again, univariate, numerical data, but now we're looking at continuous. So we're still looking at our class intervals on the horizontal axis. Our vertical is still our frequency, our relative frequency. And we're drawing a rectangle for each class interval directly above that interval. We're still looking for the center, the spread, the general shape, peaks, gaps, and outliers. So here's some data on the weight, continuous variable, a measurement of 25 airline passengers carry-on luggage. I can create a dot plot out of this data, and what I can see here is that the width of each one of these, if I make this continuous, I could use a width of 5. So what I'm doing within this width is I'm going from 10 to 15, but not including 15. My next interval would be from 15 to 20, but not including 20. And I put all the data values within that interval. And from that, I can take and make my rectangles the height of the data values, my frequency. And so it makes it easy to see how I can do this continuous histogram. We can have a comparative histogram, but in this case, you actually must make two separate ones to make comparisons. So we can see here from children watching TV, 1-year-olds to 3-year-olds, it certainly looks like the 3-year-olds, this area here is the largest from 0 to 2 hours, but it makes it easy to see. And we can also see that this would be something that would be skewed to the right. Scatter plots, time series plots, bivariate numerical data, bivariate, two variables. For a scatter plot, we draw a horizontal and a vertical axis. We label the horizontal axis and include an appropriate scale for our x variable, and we do the same for the y variable. What you have here with bivariate, you have pairs of data. And so we plot each xy point, and what we're looking at is the relationship between x and y. So the table below gives the cost and overall quality rating for 10 different brands of men's athletic shoes. So I have a cost and I have a rating. I want to see if there's a relationship between cost and rating. Well, a scatter plot, you could see this very easily than just staring at a pile of data. So you first draw and label your axis. I have cost versus rating. Does rating depend on cost? Now I plot each one of these as an XY pair. So in other words, 65, 71 would be this data point. And I do that for all of these. So I look at this and I said, is there a relationship between cost, which is my X, and quality rating, which is my Y? There appears to be a negative relationship between cost. So in other words, if I look at the cost here and their quality, so in other words, they're overcharging us for the shoes, right? Time series plots, these are nice when you have time data. Draw your horizontal and your vertical. Same thing, my X, Y need to be on an appropriate scale. I still have bivariate XY data. I connect each dot. In this case, I'm connecting the dots in order of time, and I'm looking for trends or patterns over time. So the Christmas price index is computed each year by PNC advisors. It's actually a humorous look at the cost of giving all the gifts described in the popular Christmas song, The 12 Days of Christmas. So what we can see here is there was some trends going on to 1992, but it looks like it went really down from 93 to 95. Do you know why? All right, let's look at maybe some more graphical displays you see in the media, such as a pie chart. This is categorical data. We use a circle to represent the entire data set, and each slice is a category. The size of each slice is proportional to its frequency. And this is definitely more effective when you want to summarize data sets when there's not too many categories. So the article Fred Flintstone, Check Your Policy, summarized a survey of 1,014 adults conducted by the Life and Health Insurance Foundation for Education. Each person surveyed was asked to select which of the 5 fictional characters, so 5 categories, had the greatest need for life insurance. Spider-Man, Batman, Fred Flintstone, Harry Potter, and Marge Simpson. So the data are summarized in this pie chart. So each slice here, as you can see, is a percentage of the person that was surveyed if they thought they had the greater need for life insurance. The survey results were quite different from the assessment of an insurance expert, because the insurance expert felt that Batman was a wealthy bachelor, and Spider-Man, they didn't need life insurance as much as somebody like Fred Flintstone, who was a married man with dependents. Pie charts can be difficult to construct by hand. Certainly Excel makes it a little bit easier. The circular shape sometimes makes it very difficult for comparing areas. And so what we could do is we could use a segmented or stacked bar chart. So we use rectangular bar rather than the circle, but the bar is divided into segments. The area of the segment is proportional to the relative frequency. So each year, the Higher Education Research conducts a survey of college seniors. They had 23,000 seniors participate in this survey. During the past year, how much time did you spend studying and doing homework in a typical week? So as you can see, each one of these stacked, so we're looking at 100% of people that were surveyed. This is our relative frequency. And each stack here, so the larger the area, certainly would be the larger value of how many hours they studied. Mistakes that can be made: areas should be proportional to the frequency, relative frequency, or magnitude of the number being represented. The problem is your eye is drawn to larger areas. This may not make sense because if one bucket's 19, wouldn't two buckets be 38? So using something like this, it kind of lies to you because it makes things look like they're more than what they really are. So by replacing the bars of a bar chart with milk buckets, I should say, the areas actually become distorted. Areas should be proportional to the frequency, relative frequency, or magnitude. 3 dimensions are beautiful and they look cool, but they're bad to do because they distort areas and it makes it more difficult to actually interpret. Be cautious of graphs with broken axis. In other words, the axis doesn't even start at 0. The use of broken axis in a scatter plot does not result in a misleading picture because you're looking at bivariate data. In time series, though, it can exaggerate the magnitude of a change over time. In bar charts and histograms, the vertical axis should never be broken. Never, 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 never. Be cautious of graphs with these broken axes or that they don't start at 0. So as you can see here, this bar chart is similar to one in advertisement for a software product design to raise students' test scores. Traditional instruction versus using software. The areas of the bar are not proportional to the magnitude of the number represented. In other words, the area for the rectangle 68 is more than 3 times the area for 55. It looks like a dramatic jump here, but it's really not, going from 55 to 68. Watch out for unequal time spacing in time series plots. If the observations over time are not made at regular intervals, 94, 95, 96, 97, 98, what happened to 99? So notice that the intervals between the observation are irregular, yet the points in the plot are equally spaced, but it makes it difficult to assess the rate of change over time. If you notice from one graph to the correct graph, you can now see, because of this gap, what was happening that you weren't shown quite as clearly where we skipped that gap. Be careful how you interpret patterns and scatter plots. This shows the relationship between the number of Methodist ministers in New England and the amount of Cuban rum imported into Boston. Does an increase in the number of Methodist ministers cause the increase in imported rum? Kind of looks like it, right? A strong pattern in a scatter plot means that the two variables tend to vary together in a predictable way, but it's not a cause and effect relationship. Make sure that a graphical display creates the right first impression. Look at this. Although this graph does not violate the proportional area principle, The way the bars for the none category is displayed makes this graph very difficult to read, and a quick glance at the graph may leave the reader with an incorrect impression.